Hey guys, this is Mrs. Phipps. We're going to go over how to work a series circuit. Generally, when you do, this table is a nice way of organizing your thoughts. You start with you have a column for each resistor that you have in your table in your circuit, and the total values. And then you've got your voltage, your current, your resistance, your resistance, and your power. Okay, so that's how you're going to organize your thoughts. And the concepts that we're going to use for this are that resistance in series. Sorry about my hand there, but that's what we got to deal with. Resistance in series is equal to the sum of all of the resistors. So resistor in series, equivalent resistance there is R1 plus R2 plus R3. And the reason why I'm using the phrase equivalent resistance, not total, here, is because when we say equivalent resistance, it's like saying if I were to take all of these resistors and replace them with one, what would that equivalent resistance be? So we're not quite doing a total. We're just saying we want one resistor that is equivalent to all three of those. And it'll make a little bit more sense when we're talking about parallel. But for now, that's what the difference is. We're not talking about a total, we're talking about an equivalent resistance. So we're going to use resistors in series. We're going to use Ohm's law. Voltage is equal to current times resistance. And we're going to use power is equal to current times voltage. Okay, we're going to follow these steps that are down here. They should also be on your paper. So step one is just to find the voltage. Our voltage is right where it comes out of the battery. Remember, voltage is a potential difference, so it's kind of an energy. Also, in this case, we only have one battery, so that means we only have to worry about one voltage. If there was more than one, we could go ahead and we could add those up. So step one is to find the total voltage. Step two. Okay, now we're going to go ahead, we're going to do step two, which is to write in the values for each resistors. And this stuff, we're just reading straight off of the circuit. So resistance 1 is 100 ohms. Second resistance, and I'm writing them in the wrong place. I did that all during class too. So we got 100 ohms. Let me see if I can find that symbol. All right, we're just going to keep moving. So 100 ohms, we're going to have, our second one is 300 ohms, and the third resistor is 50 ohms. Now, basically, because it's a series, all we're going to do is we're going to add them up. 100 plus 300 plus 50 is equal to 450 ohms. Okay. Now, if you're looking in the first column, you'll see that there's only one piece of information, so we can't do anything else. Same thing with the second and the third. It's only in the total column that we have any room we can do anything with. So what we've just done is we've done step 2, we've done step 3, and now we're going to find the total current. And we're going to use V equals IR to solve for that one. So since V equals IR, current will be equal to voltage divided by resistance. Okay, so we're going to take current will equal our 9 volts divided by our 450 ohms, and we're going to end up with 0.02 amps. Okay. Now, according to Kirchhoff's junction rule, that current in equals current out, and the only time the current changes if there's a junction. Look at our path here. All around here, as we go around this entire path, there are no junctions. Whoa, that was weird. There are no splits as we go all the way around here. So that means that all of our currents are the same. So the total is 0.02. Then that is also the current across the first resistor. and that is equal to the current across the second resistor, and that is equal to the current across the third resistor, and that will be equal to our total. So now that we have that, we can go back in and we just did step 4. So now we're going to come back in. We did step 5. Now we're just going to use voltage is equal to current times resistance to find these guys. Okay. So let's go ahead and just do a little bit of math so we know what we're doing. So we know that we've got voltage is equal to current times resistance. So it's going to be 0.02 times 100 all the way down. See if I can write this a little bit differently. Take this, copy it. Okay, so right here we've got V equals IR, and that's going to be, the voltage is going to be equal to 0.02 times 100. Okay, so we're going to end up over here with, whoops. All right, that gives this one 2 volts. All right, we're going to do the same thing. We come on over, and it's going to be, excuse me guys, voltage is equal to current times resistance. So in this case, it's going to be 0.02 times 300, and that's going to equal 6 volts. We do the same thing over here, and we get the same process. V equals IR. So, all right, it's the same pattern over and over again. That'll be times 50, which gives us 1 volt. Now, we were talking about Kirchhoff's junction rule earlier. You can see up here, we're going to talk about Kirchhoff's loop rule. And that is that the sum of the voltages, all right, around the circuit has to equal 9 volts. Or rather, just that we want to end up with 0 by the time we get through here. So let's talk about what's happening. All right, so if you notice, if I were to add all this stuff up, okay, so if we take our 2, we're going to take, wrong buttons, our 2 volts plus our 6 volts plus our 1 volt. What do we end up with? We end up with 9 volts. Let's talk about why that happens, how this is Kirchhoff's loop rule. Okay, so here on the left-hand side, we have 9 volts. So that 9 volts is energy that is being added to our system. So as that 9 volts comes around and it hits the resistor, that resistor is going to change some amount of the voltage. In this case, it changed 2 volts. So now 9 volts, this resistor changed 2 volts, took that kind of out of our system, and that left 7 volts coming through. Now that 7 volts hits the second resistor. That resistor used 6 volts of voltage. Okay, and so that changed the 6 volts, took it out of the system, leaving us 1 volt. The third resistor changed 1 volt. One volt of energy, and when it took it out, we left with 0 volts, which is exactly what you want to do. Because what happens if you get rid of this stuff? If you don't get rid of it, if you have leftover voltage, what happens is it keeps getting pumped back into the battery, and the battery can only handle 9 volts. And so eventually your battery will blow up or burn up or do something equally bad. So considering the conservation of energy, the energy in the beginning, all right, has to equal the energy at the end. So energy is 9 volts. All right, in this case, I said that incorrectly, I apologize. The energy in the beginning, plus or minus any changes, the work has to equal the energy at the end. Well, this is a potential difference. All right, there should always be 0. We always start from 0 and we go to 9. So we have to have, if we have 9 volts on the positive side, 0 volts on the negative side, all these resistors have to take that energy out of the system. They have to change that energy into something else. Okay, so let's go back to our table. And now we're just going to do the power. Power is current times voltage. So we're just going to do the math. So we've got 2 times 0.02 equals 4. I'm going to come over to this one. 6 volts times 0.02 amps is going to be equal to 0.12. Oh, that's wrong over here, isn't it? This is 0.04. So that doesn't look good. 0.04. Move this over so we can see things a bit better. We've got 0.04. 6 times 0.02 is equal to 0.12. And 1 times 0.02 gives us 0.02. All right. So if we add all those up, 0.04 plus 0.12 times 0.02, we end up with 0.18 watts. Interesting thing. Note that over here, so we just did this by adding these guys up. This one, the power across each one. Well, let's take it again. Powers are also just our current times our voltage. So if we were to take our total current, which is 9 volts, multiply that times our total current, 9 times 0.02, you get the same answer as if you had added them up, just as a heads up. That's kind of how you work your way around the circuit. A little bit messy, but we'll do the next batch. It's going to be kind of straightforward, and we'll work our way that way. Okay. I'm going to do the second and the third one as a second video, so just hang